anti-Markovnikov addition of HBr to alkenes, and it was found that this went with the use of initiators known as peroxides. So there's a couple more examples to show you the utility of this reaction. So again, HBr, in the presence of a trace amount of peroxide, we will get addition of Br to the less substituted end of the alkene. So that's the opposite of Markovnikov addition. And again, the bottom one, under the same conditions, will give us the anti-Markovnikov addition product. So, we've now got a way of adding HBr in two different directions to an alkene. Right, so the final classic reaction I want to look at is something called the Kolbe electrolysis. And I mentioned that nearly all the reactions we look at are chain reactions. There are just two non-chain reactions we look at. This is one of them. The Kolbe electrolysis is a non-chain reaction. It's a rare example. So it's a non-chain reaction. So what do you do in the Kolbe electrolysis? You take a carboxylic acid, you deprotonate it with sodium hydroxide or potassium hydroxide to give you an alkaline metal salt, and you then electrolyse it, and this generates radicals at the anode. What charge is the anode? Positive or negative? Positive? Negative? Both are positive. And positive. 1, 2. Negative then? What charge is an anion? Which electrode does an anion go to? So therefore the anode is positive. It attracts negative things towards it. So when we electrolyse a carboxylic acid salt at the anode wants to take electrons away. So this is an example of an electron transfer process. So at the anode, our carboxylate salt will give an electron to our positive anode. We take one away. So that's electron transfer away from the carboxylate to the anode, and that generates a radical, a carboxy radical. So the anode being positive grabs electrons. We'll see again in the next handout the carboxy radicals, well, they are resonance stabilised, but they are also apt to giving up a nice stable gas because there's carbon dioxide hidden in there. So these will be decarboxylate. In a radical fashion to give R dot and CO2. So apart from the fact that CO2 is a stable molecule, what's the driving force of that reaction? Anybody? Entropy. So you go from 1 to 2 and you're getting a gas, so delta S is good. Entropically favourable reaction. And because we're doing this at the anode, we get a high localised concentration of radicals. So unlike most radical reactions, which are chain reactions, a high local concentration of radicals means they can dimerise. So high concentration or localised at the anode, and these will undergo a dimerization reaction. So it's a very useful way of making long chain alkanes, because we can take a shorter chain carboxylic acid, electrolyse it, and dimerize it. Okay, so that's a sort of a cheap method of making long chain alkanes. So that's the cold electrolysis. Right, so those are the sort of historically useful reactions. This last one is used quite a lot even now. We're now going to start in the last two handouts looking at reactions that are useful in modern day synthesis in terms of forming mostly carbon-carbon bonds or functionalising particular CH bonds. So we're looking at what we call useful reactions involving free radicals. That doesn't mean the other ones aren't useful, but these are the more modern ones. So, useful reactions involving free radicals. Like I said, almost all reactions we're dealing with are chain reactions. We don't want unwanted dimerization reactions to take place, generally speaking, and they involve short-lived radicals. Reactive species, half-lives of 10 to the minus 3 seconds or less. So we need, for these to undergo selective reactions, we require all steps in the chain to be fast compared with any unwanted steps. And for this, each step must be exothermic or only slightly endothermic. We can't have highly endothermic processes. They won't be fast enough. So the first step, as you know, is the initiation step, and this generates small quantities. We only ever get small quantities. We only ever use a small amount of initiator, and we use an appropriate source. So, how do we make or initiate our reactions? Sources of radical intermediates. Well, the old-fashioned way is by heating something which has got a relatively weak bond. So we thermally generate them from compounds with weak bonds. And a weak bond is something of the order of 160 kilojoules per mole or less. We're opening with a relatively weak bond. For comparison, a CH bond is 400 kilojoules, so that's a strong bond. We want much weaker bonds. And two of the most common sources of radical initiating species are peroxides, ROOR, and azo compounds, which have got an NN or bond in them. Azo. And we'll look at some of these in some detail. Just for information, the peroxide bond strength in an ordinary alkyl peroxide is 146 kilojoules per mole, so that fits nicely into our required bond strength. So these are useful species for generating trace quantities of radicals, and I know one particular group are using one of these in the lab upstairs right now, diacyl peroxides. So diacyl peroxides are where we have a carbonyl flanking the peroxide bond. So typical diacyl peroxide is something of that sort. Dibenzoyl, we'll see in a minute, is one of the most common ones. And that bond is even weaker because the radical we generate when we break it is stabilised by resonance. So that's around 120 kilojoules per mole. That cleaves with a half-life of about an hour at 90 degrees C. And the reason that goes quite nicely, of course, we generate a resonance stabilised radical. And they've got degenerate resonance forms, like a carboxylate, but just a carboxy radical. In terms of arrows, that's all we're doing. Sharing a single electron with the pi bond. So that's a nice weak bond. They undergo ready homolysis at a decent temperature in terms of synthesis, 98 degrees. Right. I've just seen, of course, the carboxy radical is stabilised by resonance, but it's also rather willing to lose CO2, and that is what generally happens. So depending on what R is, and in particular the temperature. We can have entropically favourable loss of CO2. So the typical one that most people use in current synthesis is dibenzoyl peroxide. If you heat this at around 100, it will undergo homolysis and loss of CO2 in an entropically favourable reaction. So heat, homolyse the OO bond, and providing you are hot enough, that leaves CO2. Give us what we've known already is a hot radical, a reactive radical, phenyl radical, and CO2. So overall, that's very entropically favourable. We're going from one molecule, dibenzoyl peroxide, to 4 molecules, 2 phenyl radicals, and 2 CO2s. I believe a lot of you love phys chem, so anybody want to tell me why temperature is important in entropically favourable reactions? My 2 C's no. What's the Gibbs energy equation?
Delta T minus C times delta F.
Good. So if you've got something entropically favourable, T is good, isn't it? Because it makes that more important. So entropically favourable reactions are favoured by high temperature because you put more emphasis on the delta S parts of the Gibbs equation. Okay, so azo compounds are perhaps the most important source of radicals as initiators, and they in fact give us nitrogen. So a typical azo compound is as so. So like the carboxy radical, I've got CO2 hidden. This has got N2 hidden. And when we heat it, we generate stable N2 and 2 R-dots. And again, that's entropically favourable. 3 entities from 1, and one of them is gas. Delta S is very good. Right, so there's only one structure I really want you to learn in this course. Most of it's understanding, but you need to know the structure of AIBN. This is the most common initiator in modern day radical reactions, so I'm going to emphasise this. Know this structure. An example of an azo compound, and you need to know this particular structure. It's so important in radical chemistry. Azo bis isobutyrate nitrile. So it's just another example of what I've drawn above. It's just got specific R groups. So it's got its nitrogen molecule stuck in the middle, and the flanking groups are isobutyrate nitrile groups. That's AIBN. That needs to be known. Without me having to tell you. And that is a very good initiator because that loses nitrogen entropically favourably and also generates quite a nice stable radical species. So if you heat this at 80, usually in benzene, half-life is around an hour, which is a nice half-life for radical reactions. We generate N2 and a stable, relatively, radical, which is tertiary, and it's next to a CN group, so it can be resonance stabilised. So tertiary and resonance stabilised. So that's an important initiator. It's used over and over again in modern radical reactions. And we're going to see quite a few examples now because we're starting to look at more modern chemistry. And this is often used in conjunction with what's called a trialkyl tin hydride, tributyl tin hydride for example, and an organic halide. And this combination will give us an organic free radical. So this process is very common. So we have an organic halide. So what happens in this process? We start off with AIBN and we only have a trace amount of it. Remember, we only use trace amounts of initiator. Less than 0.1 of an equivalent. Heat it, probably about 80. And there's not much of it, so you probably won't see the gas, but N2 will be liberated. And we generate our initiating radical, and there's only a trace amount of this. Keep on stressing this is a chain reaction, trace amount. We have to maintain a chain process. That's got a carbon-centered radical. The beauty of tin hydrides is that their tin H bond is weak. So tributyl tin hydride is happy to liberate its H to generate a tin radical. So our trace amount of initiating radical will abstract a hydrogen to form a CH bond and a trace amount of tin radical. So again, we've still only got a trace amount of our tin radical. Tin hydrogen bonds are weak, tin hydrogen bonds are actually quite strong. So that tin radical now abstract a halogen from our alkyl halide. And there is our overall initiation process, and you'll see that repeated many times in questions and examples as a way of generating alkyl radicals. And just to show you how important bond strengths are, look at this in some detail. Then the tin hydrogen bond strength, you don't need to know these figures, but it's just to exemplify that bond strength is 251 kilojoules per mole. That's a relatively weak bond. Typically, a CH bond, which is one we're forming, is around 400. So as I said, things need to be exothermic, so that's a good step in terms of a chain reaction. You can't see all that, can you? There you go. A carbon halogen bond. If X is iodine, for example, bond association energy is 214. It's a weak bond. The tin iodine bond is actually surprisingly strong. Tin iodine bond is 270. So again, that's a favourable process. So I don't want you to learn bonds strengths, that shows you the point that every step in the chain reaction, preferably, will be exothermic for the process to proceed, even though we're dealing with very reactive species. And that, of course, is only formed in a trace amount. That's a very common way of generating carbon-centered radicals. The use of AIBN, trace, at least one equivalent of tin hydride, and an alkyl halide. Right. So we've all been informed, no AIBN structure. So that's all thermal. And those initiation events all take place at a reasonable temperature below 100 at a reasonable rate. Now sometimes our compound that we're working with doesn't like temperatures like 100 degrees C, and we have to generate radicals under a more moderate process, and in that case we can use photochemistry. So we can use photochemical generation rather than thermal, and this is when we want to generate an initiator at room temperature or below. So we're not going to bash it with thermal energy, we're going to use photochemical energy. Of course the compound must absorb light at a particular wavelength, and that wavelength of light must be sufficiently energetic for the bond to break. Now, a bit of physics, or physchem, 300 nanometer wavelength light is actually equivalent to 400 kilojoules per mole. So a mole of photons with wavelength 300 nanometers is 400 kilojoules per mole of energy. So light is quite energetic. And we get that from E equals h nu, which is also hc over lambda. And for a mole, of course, we're multiplying that by Avogadro's number. That gives you how much energy there is in a mole of photons. And that comes out at around 400 kilojoules per mole. So light is energetic, and it will initiate the cleavage of many bonds. If you ever make an alkyl iodide, for example, you often see purple generation in that compound because you're breaking bonds. And they will also cleave halogens. So a classic example of initiation is just to take bromine as your initiator and shine light on it. You shine light, bromine absorbs energy and becomes excited, electronically excited, and then that will break to give us two Br dots. So light can be used to generate trace quantities of Br dots, which can then act as a radical initiator. Azoalkanes, AIBN for example, and dibenzoyl peroxide will also absorb light in a reasonable wavelength and generate corresponding radicals. So we can use light quite often instead of heat. The only problem is you need to have specific equipment for doing this. Right, so we've got thermal, we've got photochemical. We saw Mr. Gomberg's radical last time, and that used a metal, so we can also carry out electron transfer to generate radicals. We can break bonds, or we can give electrons and then break bonds. So an example here is again a peroxide, Fe2 is iron in oxidation state 2. The more preferred oxidation state of iron is iron 3. So iron 2 is quite happy to become oxidized to iron 3 plus an electron. So iron 2 is a redox active metal and will therefore give away electrons. and many compounds, once you've given them an electron, will undergo homolysis. So iron 2 will become oxidised to iron 3 plus an electron. That electron will then go into an available orbital in our peroxide, and what R is the radical anion, and that radical anion will then split to give, for example, an alkoxy radical and hydroxide anion. So one electron reduction followed by cleavage is another way of generating radical initiating species. Again, we saw that in Gomberg's reaction, where he used silver as his metal doing a similar process. We can use metals, iron, silver, copper, to give electrons. I've just seen, of course, that the anode being positive can take electrons away, so electrolysis is an alternative way of generating radical species. For example, carboxy radicals, as was seen in the Kolbe electrolysis. So we can give or we can take. Right, we're now going to look at some very commonly used radical reactions, and these are specific ones but very common. And the first one, this will be new to you, I imagine, are thiohydroxamic esters. A chap called Derek Barton is perhaps the father of modern organic radical chemistry, and he developed a lot of this. And what he found was esters of this compound called N-hydroxy-2-thiopyridone are very good radical precursors. Let's just look at what these compounds are. So this is N-hydroxy-2-thiopyridone. N-hydroxy-2-thiopyridone. That's our alcohol component. Making an ester from it. If you would react that with an acid chloride, for example, then we'll make the corresponding ester. And that is what's called a thiohydroxamate ester. And what we've done is we've installed an entity with a nice weak NO bond. NO bonds are weak. So this is a nice precursor for generating radical species. And I'm going to show you, we're going to ramp up the level of chemistry, and I'm going to show you a specific example of how this is used in a radical reaction. So we generate a chain carrying radical that attacks at a sulfur with a thiopyridone. I'll show you this in detail, and this leads to fragmentation and cleavage of the NO bond, followed by decarboxylation. So it's quite a complex sequence of steps. I'm going to show you a specific example and leave you a bit of it to think about. So a lot of this is about problem solving. If we take this compound, this is a classic example of Barton chemistry. That's a cyclopropane with a phenyl ring attached to it. And hanging off the top, I've got my thiohydroxamic ester. that's just my equivalent of what I've drawn on the right above. So there's my thiohydroxyamic ester. We treat this with tributyl tin hydride, at least one equivalent, and a trace of AIBM, and we heat it, and we initiate a Barton reaction. And the Barton reaction results in loss of CO2, and the major desired product is just decarboxylated, which is that. So we use radical reaction to chop out a carboxyl group, essentially. We also get a second product, which is that. Now, I didn't leave myself enough space, so you need to find a bit of paper or the back sheet, and we're going to go through the mechanism of this, or at least part of it, in some detail. So that's what was found doing this radical reaction. So you find a piece of paper, we'll go through the mechanism. Bottom bit. So we're using tin hydride with its weak bonds. We've got a trace amount of AIBM, and we're heating. So we're using our azo initiation process. So if this sort of thing appears in an exam, then you draw the whole thing out. So you start off by remembering what AIBN is. Which is that. We've got a trace amount of that. We heat it, entropy is good, and we lose N2. And we generate two radicals. Trace amount. That's our initiation event. Part of it. The CH bond is stronger than the tin H bond, so that radical species will now abstract a hydrogen from tin hydride. That's favourable in terms of thermodynamics, and we generate a trace amount of tributyl tin radical. Right, so that's our initiation event. That's common to an awful lot of reactions. I'm going to shorten the structure so I don't have to keep on drawing that cyclopropane out all the time. So we're going to call this RCO right, for the sake of keeping it short. So we know we've got trace amount of tin radical. We know that our product hasn't got CO2 in it. So the standard mechanism for this is based on the fact that we want to get something aromatic out of it at the end. And we want to break a weak bond. So there's our thiopyridone. We've got a trace amount of tin radical. Tin sulfur bonds are actually quite strong. That pyridone, that heterocycle is not currently aromatic, or not very aromatic. So the first step is to attack sulfur and to generate a radical which is flanked both by sulfur and nitrogen, so it's relatively stable. still not aromatic, but we can get to an aromatic species quite easily, because that radical can eliminate and break the weak bond. We know that NO bond is weak. So if we take one electron from the NO bond and pair it with our radical species, that generates an aromatic pyridine. That's good. And it generates a carboxy radical. So like I say, steps in chain reactions have to be useful in terms of thermodynamics. So that's your byproduct in the thiopyridone. We've got a carboxy radical. We know that carboxy radicals quite like to undergo decarboxylation, and that's what happens. Minus CO2. R dot for CO2. Delta S is good. That's what is actually called the Barton decarboxylation. You make a thiohydroxamate ester and you heat it up with an initiating system. In our case, our R dot is the following. Now generated that species. We've lost CO2 from our initial compound. We've got to make a chain. We've only got a trace amount of that. To make a chain, we've got to somehow carry it with our chain carrier. We've still got lots of tributyl tin hydride left with its weak tin hydrogen bond. So that radical can now abstract a hydrogen atom, and that regenerates our chain carrier. So round and round we go in a very useful circle. So that's our chain carrier. The issue of radical chemistry is that everything is predictable, essentially, from an understanding of bond strengths and simple physical concepts such as entropy. Now I'm going to leave this one just for you to think about, but the other product from this, which you can perhaps think about how it might be made, was that. So query for next time. Right, so that's thiohydroxamate esters. You look through past papers, you'll see an example or two of that, and also in the tutorial work that's appearing on Monday. Right. So the final, less renowned way of making radical species is from alkyl mercury compounds. Alkyl mercury compounds aren't pleasant because mercury is foul and toxic, but they are very useful for generating radical species. So you take an alkyl mercury compound which has a mercury 2 species present, so that's mercury 2. We can generate R dot from that species using formally H minus. What's the most common form of H minus that you've used in the lab? Thank you. Not sodium hydride. Sodium hydride is not nucleophilic. Sodium borohydride is a source of H minus nucleophile. Commonly sodium borohydride. So an X might be a halogen. For example, or an ester OAC. So what hydride can do is it can displace X to give a mercury hydrogen bond. Now the mercury hydrogen bond is very weak. When you do these reactions, you see blobs of silver metal, grey metal, coming out of the reaction. That metal, of course, is very toxic. So these actually undergo spontaneous decomposition to form mercury zero. So a trace amount of that mercury hydride will generate mercury zero, as so. So both the R mercury bond and the mercury hydrogen bond will cleave to give R dot and mercury zero. Trace amount of H dot which will pick up a hydrogen from somewhere. This generates R dot. Trace of that happens, a trace of that happens, so this is a chain reaction again. To carry the chain, our R dot can pick up hydrogen from another mercury hydride and generate some more mercury naught. Again, we've actually seen that in the first year. We've looked at so-called anti-Markovnikov hydration alkenes. So reduction of mercury 2 halides or mercury 2 acetates with sodium borohydride gives you the alkane and mercury zero via a radical reaction. Okay, we've got around 5 minutes, I reckon. So, anybody here like films? Old films? Anyone heard of James Bond? Right. Where's my group? Right, okay. Who's this? Golf? No. Try again. He's got a gun. Huh? With what? Thank you. That's the man with a golden gun. Not relevant to this course. Anyone recognise this character? Goldfinger. Brilliant. Very sinister looking character. So Goldfinger is we're supposed to get a break every now and then in the lectures to keep your concentration, so it's quite useful, this sort of thing. Right, so Goldfinger, keep that in mind. We're going to come back to that in a minute. So last time we looked at bromination of alkanes and we found that it's not always very selective in terms of which H we can replace. Now there's a reaction called the Bowles-Ziegler bromination. Don't learn names, but this is specific for substituting allylic or benzylic hydrogens with bromine. So there's an allylic CH bond. If you treat this with N-bromosuccinimide, which is that molecule, it's got a weak NBr bond in it. Usually the trace of HBr what we get is we get selective replacement of the allylic CH heat. So it's allylic bromination, very selective simply for the allylic CH bond. Also, it's selective for the benzylic CH bond. So benzylic is that one, next to the benzyl group, the phenyl group. And again, under the same conditions, we'll get replacement . in benzylic CH. Very, very common reaction for selective halogenation of allylic and benzylic reactions. Now when you do this reaction, there's one going on upstairs, it goes brown, deep brown, which tells us something, and that tells us that bromine is formed in the reaction. So it involves the formation of bromine, and that bromine colour goes when the reaction is complete, so it goes colourless again. And finally, it's also been shown that bromine radical is responsible for the H abstraction step. We're going to stop there, but next time we shall look at the mechanism of this. Anyone else guess what the mechanism is called?